OBS.
Okay, good morning. I realized I showed you my email and it was in the recording, so like let's stop the recording and restart so you can't see my email. Anyway, all right. So we are going to start talking about Project 9. And I wanted, before I forgot, Project 9 is going to work a little differently than all the other projects, so I wanted to make sure that I kind of talked about it before I forget. You are here. We're going to be talking about this high-level language Jack today. So just like, remember when we did a project where you had to write some assembly code so that you kind of understood how assembly worked before we got to writing an assembler? So we're doing the same thing now, except we're going to do a project where you actually write some of this Jack code, which is this high-level language, so that we can then move on and understand how to write a compiler that's going to turn the Jack code into virtual machine code. Okay. So basically this week we're going to talk about, I'm going to introduce the language today. We'll look at some examples. We'll do some more examples on Thursday. And Project 9 basically is like from now until spring break. Project 9, all the other projects, it's like very exactly specified. Like you must write a program that does X, Y, Z. Here's the test. If it passes the test, good. If it doesn't, not good. Project 9 is totally different. Project 9 is like, do something cool using Jack. Okay? You can decide. It doesn't really matter what you want to do. But obviously you're limited by the language and by like the capabilities of the machine that you're running it on, which is like our hack machine. But that's what we're going to do. And I'll give you some suggestions, and you'll kind of see some examples of what's possible. So the other thing is, because next week what we're going to do is we're going to spend, I don't think we're going to have enough time to do it only on Tuesday, so we'll probably spend time on both days doing it. But you all are going to demo your project in class, okay? So this is the only project where there's no extensions, because we're going to demo them, and so like I can't really give you an extension on that because we can do. So if you wish to do Project 9, you don't have to, right? You can decide how many projects you're going to do and whatever, right? If you wish to do Project 9, then you have to actually follow this timeline. There's no extensions. So maybe you just like whatever else you're working on, you could put it on hold for a little bit, do Project 9, and then come back to Project 7 or whatever you're doing. Yeah.
So we'll be able to complete Project 9 without having done 7 and 8 yet?
Yeah, for sure. It's totally independent because, I mean, they're not even related that much because there are like a couple levels where, 7 and 8 are about translating virtual machine code, and then Project 9 is about writing code in this Jack language, and there's like a compiler in between them, so they're not even, having done all this stuff up to this point will help you understand what features are in the Jack language and like why maybe it's designed the way it is, and we'll talk some about that. But like really, even if you hadn't seen any of this stuff before, I could just show you this Jack language and just be like, this is a language, go write something in it, and you could figure it out and do it. So it's totally independent. Cool. So you'll see there's like a couple, basically this coming Friday, you have to turn in a proposal. It just says, I'm planning to do this project and here's what I plan to do. It's just like a paragraph. It doesn't have to be, it's not a lot, but just so I know that you're kind of what you're thinking about. And I'll probably come back and be like, that sounds really cool, and I don't think you're going to be able to do that because the language is really annoying. But whatever, we'll figure it out. And then next week, basically you need to be prepared to give you a demo on Tuesday because you might get picked, and you might get lucky and you might not go till Thursday, but you should be prepared. And then it's actually due the Friday before spring break. I mean, you can turn it in anytime, but if you give a demo, but it's like not quite where you want it to be, it's okay if like your demo is like, well, here's what I have so far, and it's kind of working, but it doesn't really do X, Y, Z. You have to have something that runs so you can show us, but the final deadline will be that Friday before spring break, and no extensions. Okay? Cool. Any questions about that? Makes sense? All right. Hopefully this one will be fun. Probably also a little bit frustrating because you'll see that the language, well, you'll see. The language is like, it is a high-level language, but there's also a lot of stuff that it doesn't have that you kind of are used to having. Because, of course, we need to write a compiler for it. So you will also be happy about it later when you're like, oh, I don't have to do all that I don't have to figure out how to translate all that fancy stuff that Java has. I only have to do the stuff that's in this language. So it cuts both ways, right? You'll be happy when you're writing the compiler. You'll be annoyed when you're trying to use it, but people have done some really cool things with it, so it is possible. All right, so that's the wrong page. Let's talk about it. So basically, just as a recap and to show where we're going, we have like our virtual machine layer, and then there's like, I'm not going to draw all the levels, but like there's an assembler or a virtual machine translator. And there's a whole bunch of levels under here. We all know what those are, right? Probably, many of you are working on this right now. And then there's this high-level language, which is called Jack, because it rhymes with hack, I guess, and also starts with J, which is like Java, because it's kind of similar to Java, you'll see. It's much more similar to Java than to any other language that I know of. And then there's the operating system, right, which is written itself in Jack, but provides services for other Jack programs, so they don't have to do like all the annoying things that that it provides. So this is project 9, right? That's what we just talked about. Writing the operating system is project 12. And then to translate from Jack to the virtual machine language is a compiler, which is projects 10 and 11. But actually, this is 4 projects, or it's split up into 4 project chunks, right? So I don't know. The numbers correspond to the chapters in the book, but it's actually like all of that is actually going to be 6 projects after. Well, this is before spring break, and then these other 5. Actually, even project 12, I think, is split up into 2 projects also. I think it's 6. We could check, but I don't know. If you look on the website, you'll see. Cool. All right, so that's where we're going. So let me tell you a little bit about Jack. So I'm going to tell you some things kind of in the abstract, and then we're going to spend the rest of the time just looking at some examples and running some Jack programs and kind of seeing what we can do. Okay, so Jack. It is like Java in many ways, but you'll see there's many differences as well. So it has classes, right? Everything is a class, just like in Java. Each class is in one file per class. And that, right, each class gets translated to one .bm file. Okay, so the compiler will take a .jack file, which has a single class in it, and it'll translate it to a single .vm file, which is virtual machine code. And then, of course, the virtual machine translator takes a whole bunch of .vm files and generates, spits out one giant blob of assembly. Part of the reason it's done this way is that you can mix and match. So once you've compiled a class to a .vm file, you can actually use different .vm files together, individually, without having to recompile them all as a whole. Classes have methods and functions and fields. And what is the difference between a method and a function? Well, a method is associated to an object, and a function is associated to the class as a whole. So this is like static methods in Java. basically, you know, a method would be like, you know, think about like, well, we'll see examples, I don't know. But a method is something you call on a specific object of a class, and a function is just like some functionality that the class as a whole provides. You don't call it on a specific object, you just kind of call it on the class as a whole. All right, what else? It has, so what kind of control structures does it have? So finally, we have loops. Yay! Okay, so it has if, you know, if else instructions, and it has while loops. It does not have for loops. Why do you think it doesn't have for loops?
You can just make a for loop, a while loop.
Yeah, because you can just, a for loop is really just an abbreviation for a special kind of while loop. Anything you could do with a for loop, you could do with a while loop instead. And to make life easier for us as compiler writers, we're going to leave out the for loops, all right? It actually wouldn't be that hard to add. And honestly, if you're like, if you get really into the compiler thing and you're just excited about it, and you want to try to add for loops, that could be a fun little project to try to figure out how to add for loops to the language and compile them. But that's not in the basic language. All right, so no for loops, just use while. Okay. It has some like kind of statements that you can do. You can say do, you know, some imperative thing, or like could be like calling a method, for example. You can also say let you know, x equal some expression. This is a variable assignment. So in Java or Python or most other languages, if you want to call a function, you just say the name of the function. You don't have to say do first. And if you want to assign a variable, you just say x equals expression. You don't have to say the word let first. Why do you think in Jack you have to say do something and let something? Zach?
Because we're defining, we have to tell the compiler what kind of command it is, or like what kind of expression.
Yeah, that's
to
essentially why,
expect.
right? Again, it's to make the compiler's job easier. If you're writing a compiler, you can just look at the line of code and just look at the first word, and you now know exactly what kind of thing it is. You're like, oh, it's a do? Okay, I know it's a command. Oh, it's a let? Okay, it's a variable assignment. If you think about, you know, what Java has to do, when it looks at a line of code and it sees a name, like if you see a name, you don't know yet, is it going to assign something to this name? Is it going to have an equals sign after it? Is it going to be calling it? Is it going to have like parentheses after it? Is it going to have a dot after it? So it's like an object that you're calling, right? It has to like read pretty far ahead to figure out what you're doing right now. And so we're making the syntax very simple so that you look at the very first thing on the line and you know exactly what you expect to see after that. That's going to make our lives easier when writing the compilers. Again, when you're writing code, you're going to forget. So I did this project, and all the time I would try to run it, and it's like syntax error. And I'm like, what? Oh, I forgot the word let. Dang it! I just kept forgetting the word do and the word let all the time. You're going to do the same thing. Oh well, sorry. But again, you'll be glad of it when you write the compiler later. One of the things I hope you'll learn from this is a new appreciation for how much work, you know, actually went into like when you compile a Java program or a Python program or something, like how hard the compiler is working to figure out to give you lots of nice features in Java so that it's convenient for you as a programmer. But like the compiler has to work really hard to make that possible. Here we're doing the opposite thing. We're optimizing for making things easier for us as compiler writers, not for the programmers. But in expressions, here's another thing that falls in the same category. The order of operations is undefined. Okay, use parentheses. You will forget this too. But, you know, and we'll see examples of this. If you want to say like 2 times 3 plus 7, you just got to put parentheses around everything. Because, again, it's actually surprisingly tricky to get that right. Figure out, like, based on the order of operations, like, where do I put parentheses and how do I parse this? So we're just going to say, you know what, we're not even going to deal with that. Again, if you want to learn how that works, you can, but it's we're not going to do that. What data types does it have? It has ints, it has booleans, it has arrays, and it has objects. That's it. Strings are not built into the language. There are strings defined by the operating system, just as like a class, a string class that you can use. Do you have a question, Daniel?
Is it static or dynamically typed?
Is it statically or dynamically typed? What do you think?
I'm gonna say static.
No.
No.
There's no types. I mean, like everything is ints, for one thing. And in fact, even, yeah, like if you try to assign an int to an array variable, it's like, yeah, sure, why not? It's really not typed. Again, the reason is, writing a type system, that's hard work. There's a lot of work that has to go into like keeping track of the types of everything and making sure that the types match up. We're not going to bother. I don't recall, like there's some very basic things you could do. Like you could keep track of, I think you do have to declare, when you declare a variable, you have to like declare what type it is. But it doesn't, you're not required to make use of that information later, if that makes sense. No, that's not exactly true. The reason you need to do that is because, for example, whether a variable holds an int or an array, that means when we assign to it, we have to do something slightly different. Because like if it's an int, we just like put the int right there. If it's an array, that means it's holding a memory address, and we have to go look up that memory address and put something over there. That's like the only reason that we do that. It doesn't actually check and make sure that you're using things correctly. Yeah.
About the like strings, is it unnecessary to have strings and characters? So are we like keeping it as simple as possible?
Yeah. Yeah, exactly. The Jack language itself does not really have anything about strings or characters built in. It just says ints. Now the operating system provides a string class that basically has like an array of ints that you can think of as if it's, wait, okay, no, I'm sorry. That's not quite true. How does this work? I'm forgetting now. We can actually write like strings in quote marks. And I forget, okay, so I'm sorry, I take it back. The language does support strings in that built-in way, like you can write strings in quote marks. And I'm forgetting off the top of my head exactly how that's going to work, but it does have some special support for strings. Because that would be really annoying. If you want to print out a message, you have to print like the number, like the numeric codes for the characters or something like that. How does it work? I don't remember. We'll see when we get there. Okay, and then there's this standard library, aka operating system, which has things like, there's a math library which has stuff like, absolute value, multiplication, division. There's like strings, we already mentioned. There's an output class which has things like print.
Oh.
Right? Because of course fundamentally when you want to print something to the screen, you have to go like, shove some pixels onto the screen, but there's a function that kind of helps us do that. There's like a keyboard module that lets us do things like, read line, if you want to read some input from the user, There's also a system library that has stuff like init, alt, error, stuff like that. There's some other things. There's like, especially there's some, I think there's like a screen module that lets us do things like draw lines and squares and stuff like that. But this is all in appendix, oops. I believe it is appendix 6. So you definitely want to, when you're working on this project, you definitely want to look at that appendix and see, you know, here's all the stuff that is available to you to use as you're running your program. Okay.
Yes.
Okay. Any more questions at this point? Okay, so here's our first example Jack program. This is a program to read some numbers from the user and compute their average and print out the average. Okay, so I want to go through some aspects of this kind of carefully, and then we'll actually run it and just see how it runs, and then we'll look at it, see how much time we have. We'll look at a few different examples. All right, so everything's a class. So this is class main, which is inside a file called main.jack. So basically, this is kind of similar to Java in that if you have a bunch of classes and you compile them all, how does it know what to actually run? Well, it looks for a special class called main, and it looks for a special function called main inside of main, and it runs that. And you're like, wait, I thought we called sys.init first. No, sys.init is what like the assembly code calls to like start the virtual machine. Then sys.init will call main. So sys.init will like set up some operating system stuff, and then it will then call main to start off your program. So, okay, so this is a function. You put the return type, it's void. So here's one big difference. In Jack, any local variables you want, you have to declare them at the beginning of the function. Okay? Why do you think we would do that?
It's easy.
Because it's easier for the compiler, right? Because the compiler is like, oh look, there's 4 variables, so that means I need to allocate space for 4 local variables on the stack. Great. Right? I mean, like, and you know, a real compiler has to like look through the whole function and figure out, or keep track of what all the local variables are, and then like later go back and make space for them, or whatever. So this just makes things easier for us. Okay, so you declare any local variables you want, and notice, right? See how you have to say, so you have to use the keyword var, again, so that you look at the very first word and you know exactly what it is. Then you say the type of it, and then you say the name of the variable, or you could have multiple variables. Again, the reason that the type is there is because depending on what it's storing, we have to we use it a little bit differently, right? So if it's an array, we have to go look it up somewhere. If it's an int, we can just put it on the stack. Okay, and then let's see. So right here's an assignment statement, which we have to say let. We're using this the readInt function from the keyboard class, which is provided as part of the operating system. And you see how it has, we do have like the double quotes things, so we can use strings. Clearly this looks like it's creating a new array. We'll talk more about that later, but that's provided by the array. So I guess I didn't mention that. There's an array class that's provided, that's standard, that can do a few things with arrays. Here's a while loop. Anything else to say about this? This all is pretty standard syntax for, you know, how you get, like, AI is the thing at index I in the array. Right, this would be really great to use a for loop but we don't have for loops, so we just have to say while I is less than length, and we have to say let I equal I plus 1 at the end. And then we do print string, print int. And then notice we have to say return. So every function has to return. Even if it's void, it just has to say return. And if it's going to return an int, it has to say, return whatever. Again, this is just to make the compiler's job easier because it knows that there's going to be return at the end. Because, of course, like at the level of the virtual machine, it has to have a return instruction at the end of a function, no matter whether it's returning a value or not. And you will forget this too. I forgot it a lot. This is, maybe like my second or third most common error was forgetting the return at the end of a function that was void. And I think the compiler, because they give us a compiler that works that you can use to test stuff. And that compiler, if you forget the return, it will give you an error and say, hey, you're missing a return. You're not required to do that for your compiler, but and I did do that at first, but what it meant was, instead of giving me an error, it just tried to translate it, and then it didn't work because the function didn't have a return at the end of it, and so it just kept running the code that came next, instead of jumping back to, and that was awful, right? That didn't work at all. So you'll find that there may be some things that aren't required in the compiler that you'll want to do because they'll make your life easier as you're debugging and stuff. All right. So any questions about this before I run it? Okay, so let's see. How do we do this?
This business kind of really hold whatever I want.
What was that?
I'm talking to myself.
Okay. So, so that's the Jack compiler that it gives us. I can run it on I'm going to run it on the directory, and basically it's going to take all the .jack files in there and turn them all into a .vm file. So if I run that, and then if I look at, right, so it took the main.jack file here and it turned it into a main.vm file. And I don't know, we can look at it if we want. It's not going to be super exciting, but there it is.
Yeah.
What do you have? What do you think this stuff is? Push constant 72,
Strings.
call string.append char. Push constant 111, call string.append char. It's like those strings the strings in double quotes. It had to actually translate it into, okay, create a new empty string. Now push the first character on the stack, and then call this append char function to put that char on the end of the string. Then push the next char. Right? That's how it works. So now I can load this up in the, okay, so it generated a VM file. So I'm going to run the VM emulator. I mean, if you wanted, you could take that VM file and call the VM translator on it and get assembly and run that. But you can just run it on the VM emulator. So let's load this up. Let's see. Project 9. Average. Yeah, so Project 9 comes with all these examples in it. So all these examples that we're looking at, you can go look at yourself. It's in the Project 9 folder. Just to give you some examples of some of the things. I love that. Okay, so notice this. I don't know if you can read this. I'll read it to you. It's too small. No implementation was found for some functions which are called in the VM code. That makes sense because the code that we saw, it was calling things like string.append char and output.println, right? And it's I don't know where those functions are not defined anywhere. Our .vm code didn't define those functions because those are functions from the operating system. And so it's saying the VM emulator provides built-in implementations for the OS functions. If available, should this built-in implementation be used for functions which were not implemented in the VM code? Yes, for sure, right? The point is, like, yes, later on, if we're writing our, when we're implementing our own operating system, then no, we will want it to use like the version that we wrote to see if it works. But for right now, we're like, yes, please use the built-in operating system functions that are provided. So you always just say yes to this. Okay, and now if let's say no animation, I'll make it fast, and I'm gonna run this, and it says how many numbers?
Oh,
3. Enter a number, 6. 42. 9. The average is 19. Okay, so we're in program halted. You know, and if you can step through this if you want to see how that program, and it's probably a nice idea to do this at some point, whether you do it for this project or not. But to take a simple Jack program and kind of like look at what VM code it gets translated into and how that makes it happen. Yeah, Simon.
In the Jack program for the average,
Yeah.
it uses just a slash to do division.
Yes.
How does it know to like use an OS function for division if it's not supported?
Yeah, that's just built into the compiler. The compiler knows that when it sees division, it should translate that into a call to the OS division function. Yeah. Yeah, good question. Same for multiplication, right? Because it's not built into the virtual machine, so it calls a special OS function. Those might be the only things like that. I don't remember if there's any other like operations that have to translate to special OS things, but yeah. Yeah, and notice, like, you know, if you can think about this, how did this text end up getting printed out here on the screen? Well, in the operating system, there's functions that literally know how to take characters in a string and translate them into a pattern of pixels on the screen and like shove those pixels up on the screen. So basically the operating system has like a simple font built in, essentially, right? It's like, oh, it's an A? Okay, it's this pattern of on and off pixels, and it just like puts that on the screen. All right, cool. So we can stop this. Now let's look at another example. We're going to look at square. Let's look at the main. Okay, so here's an example that has a simple little, maybe game is sort of, I don't know if it really counts as a game, whatever. It's a little interactive thing. But it has multiple classes, so the main doesn't really do much. It just says, okay, we're gonna create a variable game which holds a square game object. We're gonna call squaregame.new, so that looks like some kind of constructor. Right, it's constructing a square game object. And then we're gonna call game.run. We're gonna call game.dispose. What is game.dispose? That basically means, hey, we don't need this memory anymore. When we say .new, it's like allocating some memory for the object. And then when we're done with it, we can say game.dispose, right? You don't need to do this in Java because Java has a garbage collector that's keeping track of what objects are still being used and gets rid of them when they're not used. But in this language, again, we're not going to write a whole garbage collector as part of our compiler, so you just have to do that yourself. And it's annoying, but I mean, this is how everything used to be. And if you write programs in like C or C++, this is kind of still what you have to do. Yeah, Zach.
So when we are creating a new object, does that object get pushed to the stack?
No.
Or
objects are stored on the heap, which is that other area of memory that's not the stack, right? So it allocates some memory there, and then what gets pushed on the stack is just a memory address which points to that place in the heap. Because an object could be big, it could have a bunch of fields in it and stuff. So they do not get put on the stack. Okay, so let's look at square game. got a couple of fields, a square and a direction. Here's the constructor. So notice when you make a function, you can say method or you can say function. There's also something special called constructor. That means this is like actually constructing a new object, right? So the constructor for square game just has to initialize those two fields, right? So it says, all right, let's create a square, which we're calling square.new, something, we'll see the square class in a second. It's setting direction to 0, and then it returns this. So this, of course, just like in Java, is a reference to the current object, right? So we created this, we're creating this object, we're filling in the fields, and then we're going to return a reference to it. It has a dispose method. So what does the dispose method do? Notice, first of all, it calls square.dispose. So this square game object has a square object inside of it. So first it needs to deallocate that thing. And then it deallocates itself by calling the special memory.dealloc function. And then it returns. You can see, I hope you can appreciate that it's kind of easy to have bugs here. Like, what if we just forgot to call square.dispose? Like, nothing would go wrong right away. It just means that that memory for that square is just still sitting there, and the operating system still thinks that it's being used, and nothing else can use it. But nothing can actually, like, it's not accessible anymore. It's just a memory that will be forever used. And so if we did this a bunch, it would start filling up memory. That's called a memory leak. And that's a very common mistake, bug in languages that don't have a garbage collector. That may happen to you. It's possible. What else? Move the square. Okay, so it's worth pointing out, here is this run function. Let's make this a little smaller. How does this work? Basically, right, this game is like, it's going to animate some square and it lets you press some keys to interact with it, right? And so it says, all right, so the little tilde up there is not, right? So while not exit, we're going to wait for a key to be pressed. And we're going to keep moving the square while we're waiting. And then, right, it doesn't have built-in characters, so we just have to say, look, is key 81? Like, that's the code for Q. Is key 90? That's the code for Z, and so on. And then we just wait for the key to be released. And you might worry, what if someone hits a key and then lets go of it and then hits another key while it's still in the middle here and before it gets to here, it would miss a key press? Yes, it would, but it's so fast that it's very difficult to hit keys fast enough for it to not catch them. If you were writing a real game engine or whatever, yes, you have to worry about that, but for this, we don't care. So. Alexandria?
What if you push 2 keys at the same time?
I don't know. You can try it. I'm not sure what'll happen. Probably not what you want. I don't know. Probably it just when you have the first key down, as soon as you push the second key, it just overwrites the value from the first key, and so you can't tell that two things are both pushed down. In a real operating system will give you things like multiple events. It'll give you a separate event for when the key is pushed down and when the key is released. And so you can tell oh, the Q key got pushed down. Oh, the R key got pushed down. But I never saw that the Q key was released, so now they're both pushed down. You can keep track of that kind of stuff. But all this provides us is there's a memory location that has a number, which is what key is currently pressed. That's all it provides, so we're kind of limited. So you're not going to be able to write if you want to make some game where it depends on being able to hold 2 arrow keys at once to go diagonal, no, you can't do that, sadly. All right. All right. Let's look at square. Jack. Anything else I want to say about this? yes, the important thing to say about this is that this square class represents a square and it can draw itself on the screen. So this is the interesting thing to notice here. So there's this screen class that provides various kind of drawing functions for us. Remember, ultimately, the only way to put something on the screen is to like set bits in a certain area of memory to turn pixels on and off. So that's obviously very annoying. So it provides some things like draw a rectangle. And of course it has a loop that's going to go through and like set all the things in the rectangle, but so yeah, there's a set color function. I put color in quotes because the colors you have available are true and false. True means black and false means white, I think. So to draw a square, you set the color to true, you draw it, and you return. To erase, you just set the color to false and you draw it. And it'll just like overwrite that place with, so like to move itself, I think it'll erase itself first, then change the X and Y, and then draw itself again. Which is gonna make it look like really weird and flickery, but oh well. There's no double buffering, there's none of that fancy stuff. Anything else to say? Yeah. Here, notice, see here how there's like parentheses everywhere? We have to do this because there's no order operations, right? Also, like all the operators are a single character. Like it's not double ampersand, it's just a single ampersand means and. Again, that just makes the compiler easier because it doesn't have to deal with parsing multi-character operators. Like every operator is a single character, so it makes it easy. Anything else to say? Move up, move down, move left, move right. Okay, not much. Let's run it, huh? So let's say run the Jack compiler on Square, and then I guess here we go. So it's worthwhile looking at this. Right, so notice you see like these function commands in the virtual machine code, right? So each function definition turned into a block of code that starts with function and ends with a return. So like, here's the definition of the square.dispose function, right? It like does some stuff with pointer and argument and calls memory.dialog. If statements. Right. Let's run it. Square. Yes, that's okay. And no animation. I forget what the keys are. Oh, there we go. Whee! So I'm pushing arrow keys, and it's like making it change direction. I can push like Z to make it smaller, or X to make it bigger. Or Q to quit. So it's like reasonably fast, right? I mean, it's probably like, you know, I would say like, I have to like rewind to the beginning. Maybe like 10 frames per second or something like that, which is like not great, but not terrible. You can have a decent game that. There's also, if you want like really fast graphics, there's like some tricks you can do to make it a little faster. So literally like drawing and erasing a square every time is not like super fast. Questions? Daniel?
Can array hold whatever it wants?
Array can hold whatever it wants as long as it's holding ints. No, which is to say, everything in the language is represented as an int. Like even other objects or arrays are really just a pointer, which is I guess it's not actually 16 bits, it's like a 14-bit value or whatever. So yeah, the language is carefully designed so that everything is the same size. Everything is 16 bits. So, you know, in other languages, like in Java, for example, when you say an array of int versus an array of long, it's actually like taking different amount of space for each element in the array, and it has to do some math to figure out, like, you know, when you say index 5, it has to multiply that by the size and like figure out, you know, to figure out what actual memory address that should be at. But on our computer, you know, every memory location holds 16 bits, and in this language, all the values are 16-bit values, and so when you have an array, it just literally like index 0 is at the address, index 1 is at the memory address 1 after that, and so on. So yes, arrays can hold anything, even other arrays or objects or whatever, but those of course are represented as pointers too. Those are the things, so yeah, it's always just a bunch of ints, yeah.
Can you draw sprites to the screen, or are you limited to primitives?
No, you can draw sprites to the screen. And so there is actually, I mean, there's no like built-in support for that. But, you know, you can, for example, have an array with some ints, and each int represents like a chunk of 16 bits, and you can just like shove those onto the screen in a loop or something. And there's actually, I haven't looked at this much, but there is something in here. There's something called bitmap editor. Let me, which this bitmap editor folder doesn't have a Jack program in it. It has an HTML page. And so if you look at it, here we go. This JavaScript application is used to generate highly optimized Jack code for drawing a 16 by 16 bitmap to the screen. Okay, so you can like draw your bitmap over here.
Oh.
Right, let's draw a little smiley face. A little like sticky out, tongue sticky out of your face. And you can either choose a function or a method. So notice, maybe this is too small, but it says function void draw int location. So it generates some Jack code, which is a function that you can call to draw that thing at a specific location. And so it just like takes the base screen address plus that location, and then it calls this low-level operating system function called memory.poke, which literally just like shoves a value into a place in memory. And then it's got, see there's all these numbers here, like 576, 4100, 4088. Like it just figured out based on what bits I want, you know, like each row corresponds to a number in binary, and it's just like shoving those numbers into memory so that I get my thing. Well, let's see if we can do this. So, generic code. Even as clip desired cell, you may use 90 degrees rotation and vertical mirroring by clicking the appropriate buttons. Oh, nice.
Oh, that's kind of cool.
Cool. Yeah. All right.
I see someone with Word.
So if I copy this, we'll call it like a main.jack. I have to have a main, right? So we might as well. Class main function void main Oh, well, I need to copy paste in this. Smiley. I'll say, let's see, do smiley 50. I mean, like, even, like, this is still a little low level, because like this number that I have to give it is a location, but that's really just like an offset from the start of the screen's memory. So if you want to know like what pixel, like XY coordinate does that correspond to, you have to do a little bit of math to figure out, you know, if I want coordinates 20, 20, it's like, well, how wide is the screen and how many, I don't know. Let's just draw, I'll say do smiley 500. So if I compile this, okay. In subroutine smiley, mem address is not defined as a field parameter location or static variable. Oh, no. Oops. I put it right here. Oh, because it didn't say or into mem address. What? Okay, this thing is, alright. So, it doesn't generate exactly valid jack code, but it's close.
Boo.
I know, boo, right?
I'm suing for false advertising.
Yeah, seriously, I agree. But I'm glad we figured that out together. Let's try it again. In subroutine main. Main.smiley called is a method from within a function. Oh, I have to say main.smiley. Because it's not associated to a particular object. You have to just call it by saying the name of the class dot whatever. And the other error that I got, program flow may reach end of subroutine without return.
Oh.
I forgot return. See, I just did it. That was not on purpose. I promise.
It tells you all of the errors.
So, yeah, the compiler that they provide gives a bunch of nice errors. Your compiler, when you write a compiler, is not required to do this. Okay? Your compiler is only required to be able to successfully compile valid programs. For invalid programs, it kind of doesn't matter what it does. Because like, generating good error messages is actually super hard. It's really, really hard. Like if an industrial strength compiler, probably, you know, half the engineering effort just goes into generating good error, like understandable error messages. It's very difficult. So you do not need to do this. But it is nice. They give you this compiler, and you're welcome to use it. And it'll help because it has some nice things. And you could certainly think about how does it generate these messages. Like, you know, could you think about how you would generate them as well? So okay, we'll try this again.
I mean, it didn't.
Okay, cool. So no errors. So now we're going to load up the VM emulator, and we're going to load our bitmap editor, and we're going to say.
Oh.
See them? They're tiny little smileys, yeah. And maybe, I don't know, can we, let's see. Let's do this. Let's do something really simple. I'll just have a loop. It says int I equals var int I. And I can't say equals 0, I have to say let I equals 0. You can't, yeah. So saying int I equals 0, you can't both declare it and initialize it on the same line in Java. You have to choose different lines. I'm going to say while I is less than 1,000, main.smiley I, and I plus equals, no, first let I. I'm doing 16 because, is that the right thing to do? Yeah, because it's a 16 by 16 pixel. I don't know. I'm just doing something. Let's try this. What? No understand. What is going on? It does have my while, so notice like, there's a label in there that says something about while. So the VM code here does in fact, because I was worried, I was like, maybe it still has the old version somehow. No, this is the new version because it has a while loop in there. It has a constant 1000, right? So you can see like, there should be like adding 16 at some point. Why is it only trying them there? Well, I is less than 1000. I dot smiley I equals I plus 16.
You haven't incremented I.
I did right here.
Oh, wait.
Hmm. What? Was not expecting that.
Maybe 1000 isn't enough.
Yeah, I guess,
Is it overriding them with white?
is it
Because
overriding?
of all
is
the
it-
white space?
Yeah, I don't think so, because there's nothing like,
The light isn't transparency.
oh. Well, no, that doesn't make sense. I don't understand. I promise I will figure this out and I will explain what was going on next time. But, I don't understand what's going on right now. Certainly each smiley might like overwrite previous smileys, but I still don't understand why we only saw 2 show up when it was adding 16 every time. Because it should call it, you know, a bunch of times, whatever 1000 divided by 16 is. And those should all be valid locations on the screen.
Are there memory addresses outside the screen that aren't, or that are being set somewhere?
I mean, that could be, I think if you try to do that, I think the virtual machine emulator will crash and it'll say, or it'll give you an error, it'll say, that's not a valid screen address or something. Yeah, that's a possibility, but like the screen is, we're literally like poking into a certain memory address, and the screen is like 16K, right? So 1000, it should be much less than that. I don't know. All right. Anyway, let's see what else is in here. There's a fraction thing, which kind of has an example of like just another example of a class. This is a class that actually represents like a rational number.
Oh.
It's got like some math and stuff. Kind of cool. What else is in here? Hello world, I guess, is just like, it just prints hello world. That's kind of boring, but you know, gotta have that. List. So this actually represents a linked list. So a list object actually has some data and a reference to another list object, which is the next thing, right? So this is the standard kind of way of making a linked list. And this works just fine. You can look at that. What else is in here? I guess that's it. Bouncy is something I think I wrote. I don't remember. What does it do?
Oh wow.
Well, some of that's like the operating system. I honestly don't quite remember what it does. Okay, so this doesn't work. What? Can't find game.vm, it was right there. What are you talking about? Oh, maybe I need to, I wonder if I need to just say, load the whole directory. There we go. That's what I need to do. Okay, yeah, so that's actually an important point. If you want to run the VM emulator on something that has multiple .vm files, so as you're developing your project and you have multiple classes, you have to actually load the whole directory into the VM emulator, not just a single .vm file. It won't like recursively go out and find the .vm files that it refers to. You have to tell it, no, get everything here. So.
I see the flicker.
Yeah, it's just, there's not much you can do about the flicker. It's just like,
It just looks like a flipping coin or a spinning ball.
what was that?
It looks like a flipping coin or a spinning ball.
Yeah, exactly. Yeah, so that's a little buggy right there, but. So this was my project 9.
I'll make Tetris.
You make Tetris, yeah. It is possible to make Tetris, but Tetris is a bunch of work.
Uh-huh. I'm
Yeah,
a cute
those are
little
fun.
bear.
Yeah, it's like somehow they get close enough to each other. It just doesn't. The like, you know, collision checking is not that amazing. So it's just like, oh, they're close to each other. They're colliding. Therefore, they must bounce off in this weird, non-physically realizable direction. Whatever. It was fun. Cool. Any other questions or other things you want to see? So I haven't quite decided what we're going to do next time, but probably I'll think of some kind of example thing that we'll kind of code up together, like as a simple thing that could be like beginning of a project. Or maybe I'll think of other things that I want to show you about how this works. All right. I will see y'all on Thursday.